Hi, I'm Thuy-Duong Vuong. I will present the paper Domain Sparsification of Discrete Distribution using Entropic Independence. This is a joint work with my advisor Nima Anari at Stanford, Michal Derezinski at University of Michigan, and Elizabeth Yang at University of California, Berkeley. So we consider this problem of sampling from discrete distribution. Given the discrete distribution mu, that means the distribution over psi k subset of a given ground set of size n, we want to sample or approximately sample from mu. So how much time do we need to produce one sample from mu? For trivial mu, we shouldn't expect to get faster than n to the k time. Say if your mu support is just one element, then it takes like n to the k time to find this single element in the support. Also for approximately sample from mu, I mean like to sample from distribution mu prime that is close to mu in TV distance. So we hope that for certain family of mu, after some pre-processing, we can reduce the domain size, that is the size of the ground set, from n to some t much smaller than n, and consequently get improved runtime for the sampling task. A related problem is to count or approximately count for some family omega of psi k subset of a ground set of size n. So by approximately count, we mean that I put in h of z so that the size of omega between half z and half z times 1 plus epsilon. So one way to do that is to repeatedly approximate sample from the uniform distribution over omega. And this follows from a classical result of Jerome Vajirani in 1986. The more sample we get from mu, the more accurately we can count omega. Since we need to produce many samples from mu, we want to reduce the amortized time complexity of sampling from mu after some pre-processing step. Example distribution where the domain specification has been useful includes determinantal point processes, uniform distribution over a spanning tree or over fixed side forest of a graph or fixed side matching in planar graph. So I will define determinantal point processes in the next slide, but here I just want to remind you of the definition of matching tree and forest of a graph. So given a graph G, a spanning tree is a set of edges that form a connected and look this subgraph of G. So here in this picture, the orange edges form a spanning tree of the graph. The definition for forest is similar, but we only require the subgraph to be loopless, but not necessarily connected. So if we take this spanning tree and remove one of the orange edges, then we would obtain a forest. And a spanning tree also a forest itself, by the way. And so a K matching is a set of K edges where no two edges share the same endpoint. So here in this picture, the orange edges form a two matching. And also this graph is also a planar graph, meaning that we can draw this graph on the page without any crossing edges. So a KDPP or K-determinantal point process is defined by a matrix L, and the probability of a psi k subset S is proportional to the minor of the submatrix of L indexed by S. Here we have an example where S is a set 1, 2, and 4, and probability of this set is proportional to the determinant of the submatrix colored in red here. Usually we assume all principal minor of L are non-negative. So if additionally L is symmetric, then this means L is symmetric positive semi-definite and can be written as the product of V and V transpose for some matrix V. And in this case, the probability of a set S is proportional to the volume of the space spanned by the vectors indexed by S, and the vector is defined by V here. So for example, the uniform distribution over a spanning tree of a graph G is also a symmetric DPP with L equal V times V transpose and V being the incident matrix of G. For DPP, the traditional focus is on symmetric matrices L, but a line of recent work by Gabriel and other people consider non-symmetric matrix L for its enhanced modeling power. Both symmetric and non-symmetric DPP has many applications in a wide variety of fields, including in machine learning, such as in recommender system and in image search, and also in randomized linear algebra. You can refer to the many papers of Will and Water, Tasker, Garrer, and Derezinski, and other people to learn about the definition of symmetric and non-symmetric DPP and the application. So I will mention a brief history of the domain classification framework. So this live work started with a work by Duffy, Peoples, Penn, and Rao in 2017, where they use a similar domain classification idea to count spanning tree in graph in quadratic time. Morrison's work includes exact sampling of symmetric determinantal point processes by Derezinski in Code 19, and then by Calandriello, Derezinski, and Vuong in 19 and 20. And then the fourth paper last year by Nima and Michal and Derezinski get a similar result for on log concave distribution, which includes symmetric determinantal point processes. So this previous work only apply to distribution that satisfy log concavity, a very strong assumption with roughly mean that the hypergraph associating with the distribution is a very strong high-dimensional expander. Our work obtained a generalization of Nima and Michal's fourth paper for a much wider class of distribution, which include non-symmetric DPP and distribution over fixed size matching, as well as all distribution considered in the previous work. So the distribution all fall under the class of entropically independent distribution. And the notion of entropic independence were recently introduced by Nima, myself, and other co-authors, and turned out to be the right assumption for the domain classification scheme to work. So we will go on a detour briefly and talk a little bit about sampling from continuous distribution to get some ideas for our case. So there's this framework for sampling from continuous distribution where you can sample from a continuous distribution whose density function is both log concave, and then f is also in an isotropic position. So for continuous distribution over the d-dimensional vector space, f being in the isotropic position means that the mean of f is a zero vector. The mean of the vector taken according to the distribution defined by f is a zero vector, and the covariant matrix is the identity. Also, for continuous distribution that has log concave density but not in isotropic position, we can do a transformation like scaling or shifting the domain to put it in an isotropic position. Anari and Derezinski fourth paper last year so that we can obtain an analogous framework for discrete distribution. So Anari and Derezinski say that a discrete distribution mu is isotropic if the marginal of its element are roughly the same, where the marginal of element I is defined as the probability of I being included in a set S when we sample S from mu. So there is a very simple procedure that converts any distribution to an isotropic distribution. The way it works is suppose we know the marginal of the element. So here we have the element from 1 to n with the blue column denote the marginal. And the higher the marginal is, the taller the blue column is. So we see that 6 had a very high marginal. So the natural idea, maybe we can split 6 into many smaller copies. And now each smaller copy will have roughly the same marginal. The thing is, this operation is like splitting the column into many smaller squares of the same size. So the next question is, of course, how can we compute the marginals? For determinantal point processes, this is equivalent to some linear algebra that can be done quite efficiently. And generally, we can compute the marginal by sampling, then use the counting to sampling reduction of Jerome Vajrani and Vajrani. There's also a more delicate annealing process that gets things done faster for special class of distribution. And for that, you can look at Michal and Nima's fourth paper. But here our paper also improve upon previous work in the pre-processing step, because we only need to estimate the marginal within a constant factor, whereas previous work need to either compute the marginal exactly or estimate the marginal within inverse polynomial precision. But I won't go into the technical detail here. Okay, so assume we did this isotropic transformation. So how can we use isotropy to accelerate sampling? So here we have a very simpler idea of intermediate sampling. So we take a subset T of element of the domain, and then we sample from mu restricted to T. Then instantly you reduce the task of sampling from side N domain to side T domain. The problem is this doesn't quite work. So for many distribution of interest, we need to set the size of the set T to be huge in order to get anything that is sufficiently close to the target distribution mu. Okay, so this is nice, but it doesn't work. So how can we fix this? So we will repeat this process a few times. So we start at S0, we sample some S, T or rho uniformly at random, and then we add it to S0. Then we downsample to get a new set S1, and then we repeat the process with S0 replaced by S1. So we repeat the process a few times, and the gain is that we can get inverse polynomially close to the target distribution mu by repeating the process only log many steps. And this is a nice thing about the Monte Carlo chain, about the Monte Carlo Markov chain method. So, and then also each step of this intermediate sampling Markov chain can be implemented efficiently using the local random walks introduced in previous work by Ali Muhammadi, Nima, Kiran, Kumar, Siragar, and I in stock this year. Okay, so so we need to learn like how small can we make the size of set T be. So let's get some intuition. So consider this distribution mu on subset of side 2 of the set of the vertices that is defined by a bipartite graph G. So mu is the uniform distribution over the edges of G. So consider a random subset T of the vertices. For there to even be one edges contained in T with non-negligible probability, we need T to have size roughly root n by the Berkeley paradox. Okay, so on the right is the bipartite graph. And more generally, for distribution on subset of size K, we need T to be at least n raised to 1 minus 1 over K to get even a single object in the support of the distribution. So to see that, consider the case when mu encode a hypergraph where each hyper edge contains K vertices in a similar fashion to the mu in the previous slide that encode a bipartite like general graph, like normal graph. Then now the question is, okay, so it seems we can get from a domain of size n to domain of size n raised to 1 minus 1 over K, but can we do better than that? Can we get T to be some sublinear function of n that whose exponent doesn't depend on K? For example, say T equal to n raised to 0.9. And the answer is that we can for many distribution of interest. And we will formally define the class of such distribution next. So we will define entropic independence. And we begin by defining the generating polynomial of a discrete distribution. So for distribution mu, let each generating polynomial f mu be the multivariate polynomial on variable z1 to zn. That is defined as the sum of mu of s times the product of zi for I in S. And here we can think of f mu as extension of the density function mu supported on discrete subset to the entire real space R to the n. So now finally we are ready to define entropy independence. a distribution mu is entropically independent if the transformation of the generating polynomial is bounded above by its tangent at the point z1 to zn equal on 1. So here the transformation is defined like this, and this pi, which is the marginal of the element I divided by k, is actually also the first derivative of f of mu as zi, and where all the z1 to zn are set to 1. So this definition was introduced by Nima, myself, and Michal, Fred, and Huy in a paper this year. There's also an equivalent definition in terms of the entropy conduction of a certain operator called the Dow operator that sends a set of size k to a set of size 1 by selecting an element uniformly at random. But we only need the first definition for this talk. For further explanation about entropy independence, please refer to the talk I gave at ETH with the video recording on YouTube. So the intuition about entropy independence is the higher the parameter alpha is, the stronger the entropy independence assumption. So this means that if a distribution is entropy independent with parameter alpha, then it is also entropically independent for all parameter alpha prime less than alpha. So one thing that is nice is that all distribution over sets of size k are actually entropically independent with alpha at least 1 over k. And you can prove this using Cauchy-Schwarz. Some example of entropy independent with higher parameter alpha, especially with alpha being at least a constant, include the spanning tree distribution, the symmetric and non-symmetric determinantal point processes, and the distribution related to k margins in graph. And the last point I want to make here is that the isotropic transformation scheme we discussed earlier preserve entropy independence. So we can assume that our distribution is both entropy independence and isotropic. So now we are ready to state our main result. We saw that for 1 over alpha entropically independent mu, we can reduce the task of sampling from a distribution over domains of size n to a distribution over domain of size n raised to 1 minus alpha times some poly k factor. So application of the Bow theorem include faster algorithm to count size k matching in planar graph, and also faster algorithm to sample from non-symmetric and symmetric DPP. Also we also saw that for all distribution after some pre-processing, we can always reduce the domain size from n to n raised to 1 minus 1 over k, and this matches the birthday paradox threshold in the example that I talked in the hypergraph example that I talked about earlier. So we discussed some high level. So we also saw that the domain size we obtain is tied for entropy independent distribution in terms of the dependency on n. The lower bound construction we have here is based on Rich-Solomon code. Our lower bound still apply even if our pre-processing step allow access to higher order marginal of mu. Next, we discuss some high-level ideas of the proof. We will show that in one step of the intermediate sampling Markov chain, we get within constant distance of the desired distribution mu. That means after apply one step of the Markov chain, starting from any set S0, we get a set S1 whose distribution is within 0.1 of mu in terms of TV distance. Then this will imply that for any epsilon, we can get within epsilon of mu in log of 1 over epsilon step. So if epsilon is inverse polynomial in n, we can get like within epsilon of mu in log n step. So okay, so now our task is only to prove this inequality. So after some transformation and change in inequality, we can lower bound this ratio by this expectation formula raised to the power of 1 minus 1. And now we want to upper bound this expression star. And the nice thing about this expression is that we can rewrite it in terms of the transitive polynomial of mu. And now we can apply the entropy independence definition to upper bound this polynomial by the tangent, by its tangent at the point on one. And then because the tangent at the point on one is related to the marginal of each element, and we know that the marginal of each element is roughly 1/n because of the isotropic assumption. So we can bound this entire expression, and then by choosing a suitable t around n to the 1 minus alpha, we are done. So to conclude, domain specification is a useful scheme to produce many samples from a distribution in faster amortized time. So this in turn reduces the time complexity of many counting problems that utilize the classic approximate sampling to counting reduction, including the problem of counting k-matching in planar graph or counting side k-forest and so on. So our work will generalize the domain specification framework considered in Anari Derezinski's Fox paper. A remaining open problem is whether we can reduce the domain size to be independent of n. We know that this is true for symmetric DPP and distribution over base of rank K matroid through previous work. We conjecture that this is also true for K matching and non-symmetric DPP, and more generally for all alpha functionally log K distribution, if we allow a preprocessing step where we are given access to higher order marginals. So that is the end of my talk. Thank you.